Start recording. Well, let's continue. Okay, in the problem that we solved in the last lesson, there is a second part where uh, where the question is there a displacement current in the air? If so, calculate it. Well, the part B. So solve in order to solve the question in the part B, we need to know the displacement current density and displacement flux density first of all. After that, displacement current, we find displacement current density. Well, in the air, electric flux density D is the same as in the dielectric. So it comes from D1N equal to D2N. So the D air is the same as before, as we found D for the electric here. D is the same, so if D is the same, the displacement current density will also be the same. JD will also be the same and will be equal to 136.3 cosine omega t ampere per meter squared. And where omega is 4.9 p 10 to 9. Okay. Well, now let's move further and okay, this is the now we introduce the Maxwell equations in integral form. Well, the equations that we introduce here, all these field equations, were in differential form. However, the uh, differential forms of equations are not always suitable because for the calculation of fields and field related quantities, uh, an integral form of equations are more convenient and sometimes of the more descriptive of the phenomenon involved. Okay, now uh, in order to introduce integral form of uh, equations, we start with the equation 11.6, which is this. Okay, well, resume recording, and we start with the equation 11.6. Okay, rotor of H, the rotor of H is equal to J plus D over the T. So J plus displacement current density. Now, if we apply integral over the surface S to the both sides, integral over the surface S equal to integral over the surface S J ds plus integral over the surface S over the T. So ds. And now what we have? We apply Stokes theorem here. When we apply Stokes theorem, we get rotor of H ds will be equal to the integral over the closed path C of H dl, or dl or dr, it doesn't matter. Okay, and now okay, now what we have? We have this term is equal to I. In this case, let's call it IC, conduction current or conducting current, and this term we said JD, therefore displacement current density, therefore this whole term will be ID, displacement current, and our equation becomes so integral over the closed path C H dl equals to conduction current IC plus we can write ID, or let's write for now this is the integral form of the of one of the Maxwell equations, uh, and this equation also we know this equation also as Ampere's law. Okay. Now, if we look to another equation, for example, equation 11.5. 11.5, equation 11.5 is so rotor of electric field intensity is equal to minus the B over the T. Okay. Okay, now if we apply the integral to left hand side and the right hand side, integral over the surface S equals to minus the B over the T over the surface ds. Okay, similarly to the previous one, this become as integral over the closed path C E dl. Yep. And what about this? This one gives us the df over the t, and this will be equal to minus df over the t. Uh, this equation, this equation known as Faraday's law. So similarly, we can write the integral forms of equations 11.7 and 11.8. Okay, 11.7, equation 11.7 is divergence of D equals to rho V, and okay, let me write divergence of magnetic flux density equals to 0. Now, here we apply the volume integral to V equals to volume integral of rho V dV. Okay, this integral gives us simply the total charge Q. And in this integral, we apply the Gauss, not Gauss, sorry, we apply divergence theorem. When we apply the divergence theorem, we switch from volume integral to surface integral, and ds is equal to the total charge q. Okay, this is another equation, and this equation is Gauss's law. Okay, and final, uh, if we look to the final equation, what we have, let's here also let's apply volume integral of divergence of B is equal to, okay, 0. And if we apply here the divergence theorem, we have integral over the closed surface S B ds equals to 0. This is our final equation. Okay, this equation shows us that there doesn't exist there doesn't exist monopoles in nature. No monopole. Okay. Now, okay, now the we may look in the table which concludes table summary of electromagnetic field equations in differential and integral forms. So if we paste it here, okay, the Maxwell equations, Faraday law, differential form, integral form. Ampere law, differential form, integral form. Gauss's law, differential integral form. Law of no monopoles, differential form, integral form, and some constitutive relations between B and H, D and E, and Lorentz force equation is this. Okay, this is the summary of electromagnetic field equations. Well, now we can save. Now let's see one problem. Okay, this is more or less theoretical problem. Nevertheless, let's copy it and paste here. So, show that if j equals 0 in equation 1129 and q equals 0 in equation 1130, two divergence equations in 1130 and 31 can be obtained from equations 1128 and 29 without need to invoke the continuity equation. Okay. We are given that j equals 0, q equals 0. It means in 1129 j equals 0. In 1129 j is given as 0, j is 0. So in 1130 q is equals 0. Now we need to derive equations 1130 and 1131 from equations 28 and 29. Okay, let's proceed. So we know that 24 and 28 are the same equations. So let's take the divergence of uh, this equation. So what we have, we will have a divergence of electric field E will be equal to minus divergence of dB dt. So sorry, dB dt. Now let's hide this layer. Okay, what we have? Okay, what we have? And for any vector field, divergence of curl of that vector field is 0. Now let's work with the right hand side, and what we have? We have minus d dt of divergence of B. And from here it comes that divergence of B is 0, and if we wait and divergence of B is 0, and if we apply the volume integral V of divergence of be the V, and here we apply uh, divergence theorem, and it becomes the integral over the closed surface as b ds is 0, and from this, yeah, okay, that's it. Uh, we have derived equation number 1131. Okay, we have derived equation 1131. Now, next. Next, let's take equation 1129 or equivalently equation 1125. Sorry, let me write here 1129 or equivalently 1125. And what we have, if we take the divergence of rotor of H equals to divergence of J plus divergence of d over the t. Yes. Hmm? Here, J, okay, J is given as 0. J is given as 0, so this term goes away. This is again is 0 because the divergence of curl of vector field is 0. What we have now? We have divergence of d over the t equals to 0, or let me write d over the t of a divergence of d 0, and it means that divergence of d also 0, and now here we apply again volume integral v of divergence of d and this is equal to s ds according to the divergence theorem, and okay, ds, all this equal to 0. And we conclude that of s d d s equal equal to 0. And if we look to our equation number 1130, equation number 1130 is equal to q. This is equation 1130, and for q equal to 0, this equation becomes s d ds equals 0, which is exactly the same equation. Okay, do you have questions, problems, misunderstandings? Okay. In that case, I stop recording.